Thank you. My name is Marc Canel. I'm with ARM, and I'm working on the security systems at ARM. I've been at ARM for almost 3 years, and working on security systems is a fancy way to say I'm working on Trust Zone and the Trust Zone ecosystem. Before ARM, I was at Qualcomm. I spent 18 years at Qualcomm working on software, various software projects. And during the last 3 to 4 years, I actually also worked on security at Qualcomm, most notably Trust Zone and the Trust Zone ecosystem. So I've been working on Trust Zone for the past 6 years, roughly. Before Qualcomm, I was at IBM. So I want to talk to you about this Open Trust protocol that was developed between several companies. And you see the names of people from Solacia, which is a Korean card company, but they're also a TEE developer. You see names from Symantec that you probably recognize. They are a big certificate authority vendor. And then finally from Intercede. Intercede is a company which has some identity solutions, and they also have a trusted application manager. So all these companies got together about 2.5 years ago and decided to put together this Open Trust protocol, and we actually have a first iteration of the standards document, and I'm going to take you through why we did it, what we did. So the 4 companies that I've listed so far, ARM, Solacia, Symantec, and Intercede, were the founding companies of this project. They're the founding members. And we recognize about 2.5 years ago a common problem around how does an application manager access the applications within a Trust Zone within mobile devices. We had actually all worked in previous, I would say, projects prior to OTrP. When I was at Qualcomm, I was already working with Symantec and Intercede, and of course with ARM at that time. And so we realized after the initial Trust Zone projects of 4 or 5 years ago that we actually needed to do something. We needed to create a messaging protocol that would be a standard to build trust between devices and between connected devices and backend system. And we needed to have a common mechanisms to do application management in a Trust Zone. We wanted to, of course, do all that stuff over the air. So we didn't want to reinvent security mechanisms and concepts. We wanted to just define a messaging protocol, and we wanted to reuse existing standards. And so we reused the public key infrastructure, which is a well-known security mechanism. And we wanted to make sure that I would say the protocol that we build, that creates an end-to-end security chain from the firmware of the mobile device to the TEE, to the Trusted Application Manager, and to the TSM and service provider. What we also wanted to make sure is that there would be no one party that would actually have the ability of creating a situation of monopoly for itself, one vendor which would be able to monopolize one aspect or another of this end-to-end chain. And most important, we wanted to make sure that multiple certificate authorities could actually play within that chain of trust. So we have achieved a first step of our goal, which is we released an RFC draft to the IETF at the beginning of July, and we have actually submitted the Open Trust Protocol to a global platform for fast-track approval. The slide says we are considering submitting the protocol to global platform, but The protocol has been submitted to global platform and global platform has accepted to fast track that protocol. Probably within the next 6 to 8 months, OTrP will become a global platform standard. So let's talk a little bit about the problem that we wanted to solve. That slide shows what is at a high level the architecture which was typically implemented by multiple parties within the ARM mobile ecosystem, starting, let's say, 5 years ago. You would have a device split between trust zone and its normal world. You would have an agent implemented through an SDK of the TAM vendor within the normal world, and then you would have a TEE environment. Service provider makes a deal with the trusted application manager. The trusted application manager then pushes applications through its agent within trust zone. Applications that we're talking about, digital rights management, identity management applications, payment applications, and in some other markets, you can imagine, broad set of applications. In the mobile world, it initially centered around entertainment, protection of entertainment content, protection of privacy and identity, and payment. The problem is that most of those systems were actually walled gardens, proprietary ecosystems. So you would have one TAM vendor creating an agent in the rich execution environment of the TEE, but it was a proprietary protocol. Sometimes the security model was actually also proprietary and known, and that created a lot of problems for the service providers that were looking across the mobile ecosystem and later down the road across the IoT ecosystem to, I would say, consistent security models and consistent implementations, consistent protocols to access applications within trust zone. And one of the best examples of actually the consequences of that situation is the big credit card companies in the Western world refused to then put card credentials in trust zone because they couldn't find consistent security models. They couldn't find consistent mechanisms to access the card information, and they decided to put the credentials up in the cloud, and they created something called host card emulation. So down the road, especially looking at the IoT marketplace, we decided that we wanted to fix this problem. We saw that there would be actually growing fragmentation in the mobile market, in the IoT market, if actually we didn't take a leadership position between ARM and several partners, especially Symantec, which is a very big certificate authority company, and we proposed to the industry a protocol that would actually standardize the way trusted application managers talk to secure domains in trust zone, how those secure domains are set up, how they're authenticated, and enabling also very important for multiple certificate authorities to push their certificates in those secure domains to authenticate the secure domains. So we looked at I would say, the ecosystem, the environment, the landscape. There was no standard. We didn't see anybody leading to actually define a standard, and so we decided to take a leadership position here. So what we wanted to achieve was build a simple trust and provisioning mechanism between service providers and connected devices. We didn't want to be actually tied to a specific hardware execution environment. Yes, there's some underlying requirements that were defined later down the road on the implementation of those hardware environments, but at the end of the day, if you have an isolated execution environment, if you can load a couple of root certificates within the devices during manufacturing or at some point in time during the provisioning process of the system, then you're good to go. This protocol is going to work for you. We wanted to create a free specification for industry use, so it was not about creating another proprietary protocol, another proprietary ecosystem. It was about building this protocol, designing the protocol, and then releasing it to an international standards body. We also did not want to reinvent security schemes. We all felt comfortable with the concepts behind asymmetric keys, behind the public key infrastructure, behind certificate authorities infrastructures, and we wanted to reuse those mechanisms and just build a simple messaging protocol on top of them. Want a high-level protocol. So here's the basic concept of what we achieved. It's an open and secure framework, open in the sense that you can all go down now on the IETF website and download the document that describes this protocol. It's the version 1.2 of the protocol. It's an over-the-air management framework. It enables a trusted application manager to dynamically define in a mobile device a secure domain and use keys of multiple certificate authorities to authenticate that secure domain on behalf of a service provider. We use, as I said earlier, the public key infrastructure. The mechanism is, of course, based on having trust anchors and certificates provision within the TEE device, within the trusted application manager, within the service provider, and we'll see a little bit later how that works. Attestation is taking place between the TEE and the trusted application manager, using key pairs, using certificates to control remotely the integrity of the applications that the TAM is talking to. But a TEE device can be provisioned to recognize several TAMs. Right now, we don't have a hierarchy within the protocol between TAMs. Maybe later down the road, we define hierarchies between TAMs. We'll have to see that. So multiple certificate authorities can actually work with both the TEE vendor and the TAM and the service provider. So we have created a mechanism which is based on a known system, the PKI infrastructure, but allows multiple certificate authorities, multiple TAMs, multiple service providers to access devices. Now, there's a certain level of pre-provisioning that needs to take place, but it's actually open. Nobody actually owns, I would say, a toll booth anywhere within the system. It's a complex ecosystem, all right? It looks easy when you take a look at the previous slide, but actually at the end of the day, when you try to implement things, there are lots of players involved. You have a service provider, you have a trusted application manager, you have a key management architecture, you have a key infrastructure that needs to be built in order to achieve attestation between the various parties. You have a trusted execution environment provider. Sometimes it's the same party than the device manufacturer or the OS the developer, but sometimes not. You have the trusted firmware provider. The trusted firmware provider will work with the chipset vendor or with the OEM of the device. But you're dealing with multiple parties here, and one of the reasons why this protocol was important is that all these parties can get together, in one room, and for one specific application, define one implementation. But if you try to have some level of harmonization between all these parties, an international protocol was actually a requirement. So here is at a very high level, the solution that we have. The Trusted Application Manager builds an SDK based on the Open Trust Protocol. That SDK gets embedded within the normal world of the client device and communicates with the TEE over the trusted firmware. In the ARM ecosystem, ARM delivers for Cortex-A what we call actually trusted firmware. It's an open source project and reused by most of our customers and partners. Then a TEE vendor will integrate their own secure OS with an implementation of the OTrP protocol, and of course would integrate that with the SDK of the TAM. At provisioning time, all the parties will then load the keys from the certificate authority so that everybody has a way to recognize everybody. But multiple certificate authorities can work with all those parties. There's no one point of control. So the certificate authority has to issue keys to the TEE vendor, to the trusted services manager that runs the TAM, to the trusted firmware vendor, which is very often actually the company that manages that is the chipset vendor, and the service provider. So what does the spec contain? It actually defines the trust relationship between all these entities. And the underlying mechanism is the public key infrastructure. Right now, the trust relationship is from TEE to TAM to service provider. We have not yet worked out any mechanism for trust relationship between the TAMs. Maybe this is actually an iteration within the development of the specifications. So we decided to reuse JSON messages to build the protocol. Again, we didn't want to, invent anything from scratch. We tried as much as possible to reuse known technologies. And so we have a set of JSON messages to define device attestation so that the device attests its identity with the TSM and for the device to trust the TSM. We have messages for security domain management. So in other words, a trusted application manager can request to create a secure domain within the trust zone execution environment of the device. Then that domain will be identified with, of course, the keys of the certificate authorities that the TAM is working with. But multiple certificate authorities could be used to create multiple domains within one device. Of course, you have messages for trusted application management, so basically download and then update. And then you have some messages for network communications. Yes?
You have a certificate from the service provider and TAM to the device. Are you also expected to require a certificate that you need to have the device so it can send that certificate up to the other bit?
To where?
So in other words, you have to, are you guys having an option to take these in the device that can tell the service provider, I really am this person?
Yeah, absolutely. We have that. I have a slide later that shows all the certificates which are within the system. Okay? There is an agent, an OTrP agent within the rich execution environment, because of course communications take place with a rich execution environment. We're using the standard PKI artifacts and algorithm and JSON messages and JSON security RFCs. So it's all based on stuff which is standard. So the architecture of the system is for the CA to issue certificates to all the OTrP components, which are the TEE, the Trusted Application Manager, the trusted firmware of the device, and the service provider. The TAM vendor provides an SDK to communicate with the TAM from the client application. And the TAM will communicate with the OTrP agent to relay the OTrP message between the TAM and the TEE. So there is an integration job that needs to be performed by the SoC vendor when putting this architecture together. Yes? Yes, TAM and TSM gets used very often in this presentation interchangeably, absolutely. Right, right. Okay, so the specs, the scope of the specifications is from the TEE to the OTrP agent, to the client, to the TAM. It actually also defines APIs between the agent and the client applications, okay? And here you have the certificate authority enrollment API. So certificate authority enrolls the TEE, the trusted firmware, which gives you, the root of trust of the device, and then of course the TAM. The OTrP agent is responsible for routing the OTrP messages to the appropriate TEE. It's developed, distributed typically by the TEE vendor. Actually, no, that's a mistake. That should be developed and distributed by the TAM vendor, because it needs to be able to talk to the TAM. But it gets integrated typically between the TEE vendor and the SoC. And it's implemented it implements an interface as a service, an SDK, to the TEE. This is a list of JSONs that are referenced within the protocol. I'll let you go through that list. I don't think that I need to really describe it. And so the benefits of OTrP is we see a standardized mechanism for built-in trust and privacy. That's actually very important to have that consistent mechanism for trust and privacy for service providers. This was one of the big issues of the card companies, Visa and MasterCard. It's also interoperable with fairly easy adoption because it reuses the PKI infrastructure, it reuses JSON messages, so you have a lot of developers that have experience with those technologies. We all know also from the PKI architecture that it is actually scalable, so we have an architecture here that scales fairly easily, and there is no vendor lock. No one vendor actually owns this system and can put a toll booth within the system. Service providers can then focus on their applications and defining the application that they want to work on. There was an initial focus on the mobile marketplace, especially around identity management, but we see it actually also now being applied within the IoT marketplace. There have been some reference implementations that have been demonstrated. They were actually built by Solacia with some applications from Intercede. And it was an identity management application, was presented at MWC earlier this year, and then at the ARM Partners Conference in the August timeframe also this year. So, I will put up the slides that answers your questions on the architecture of keys. So, keys are generated by the certificate authority. The service provider will have its key pair and the certificate. The TAM will have a key pair and certificate. The device TEE will have two key pairs, one for the TEE and one for the trusted firmware. Then the service provider and the TEE will have derived keys that are used for encrypting the binary data. And then you will have trust anchors with the TAM and the device TEE. So the key pairs of the service provider will be used to sign the trusted application. The key pairs of the TAM will be used to sign the OTrP request, which are passed to the TEE. And the key pairs of the device TEE will be used for device attestation to the TAM and to the service provider. And the device, the key pair of the trusted firmware will be used for attestation and certification of the device itself. So that's the architecture. That's how the PKI infrastructure and architecture is reused within the OTrP protocol. And then, look at this architecture of keys. Assume that you have a layer, a messaging layer on top of that, and which is implemented using the JSON messages and protocol. Question? Yes?
The PKI infrastructure is being a well-established, safe, existing thing. But the reality is that one of the things problems with PKI infrastructure today is when you have a root certificate or some GA certificate is compromised. Mechanisms for dealing with that really suck. You have to have a replication list, you have to do this whole protocol. But have you guys got something new that can make this problem?
No, we have not yet looked into that matter. We understand that. We understand that the problem of revocation is actually a big issue, but we have not looked into that. There are some other problems that we need to fix first. We need to have a common messaging system. But the problem of revocation is actually an important problem, especially when you get to the IoT marketplace. Yeah, it's big. Understand that, yeah. We are at the version 1.0 of this protocol, and one of the reasons that we actually wanted to go, I'll get to you. One of the reasons why we wanted to go to open standards is that, we were 4 companies, we had certain skill sets and certain level of experience, but we can't get to a complete global peer review of the system if we don't go through a standards body. And Global Platform was actually quite keen on us coming within their system. So yes, so the agent would be updated within I would say, a process typically managed by the OEM. The OTrP agent is part of the code that's delivered by the OEM, okay? So if you actually, if I were to go back in some of those slides and I look at the stack of code which is in the OEM device, the OEM has actually a fairly important responsibility within this process, okay? It needs to sign the code that you will find either within the rich execution environment or within the trusted execution environment, and it needs to load the initial keys, master keys and of either the device, the trusted firmware, or the TEE. So it will be through, the OTrP agent will be updated through an OTA process managed by the OEM, okay? There's one thing that I would like to point out here. is that this system is completely independent of the underlying communications mechanism. OTA is any communications protocol, doesn't matter. Okay. Yes.
Another issue for, especially for IoT devices, maybe, I'm not sure if you've ever seen these demos, but I've seen people do it. Where if they get access to the device, they can basically crack cryptography if they can help with the power, using the power analysis and stuff like that. Of course, there are some ways to solve that, but usually you need to get some hardware support, but not software. Again, is ways talking about that thing, are you going to require some hardware or yeah?
So you're bringing up a topic that we actually looked into when we designed the protocol. We designed a protocol. We did not design the implementation. And so the implementation and the level of countermeasures that you actually put within the device to protect the device against side channel attacks or again other hardware attack was actually not the, I would say, the objective of the design of this protocol. Okay? The idea here was to create a standardized mechanism that all parties could use to set up secure domains and manage the content of those secure domains. But you can deal with devices where you have very expensive data and you need to have side channel attack countermeasures, and you can deal with devices which the data is not worth much, but you may have millions of these devices. But you cannot afford on a device per device to put side channel attack countermeasures. So we designed a protocol, we designed an interface. We did not want to get into the job of the individual OEMs and the individual application developers. Okay?
Do you have a similar slide that shows the domain
No, there's actually no hierarchy between the trusted domains. Okay. Right now, they are all, I would say, running in parallel on top of the trusted OS. As I was saying earlier, we don't have a concept of hierarchy between the TSMs, and I should add, we don't have a concept of hierarchy of secure domains within secure domains. We don't have that yet.
Technically, there's an infrastructure domain that's essentially the trust execution OS.
Right.
And then beyond that, the hierarchy is that it has to then authenticate or authenticate the additional domains that work on.
Right. Right, but we don't have, I thought your question was whether we have secure domains within secure domains, with delegation of authority. No, we have not covered the concept of delegation of authority within a secure domain. That's one of the things that we need to look into, yeah. Right. Yes?
Does this architecture allow for TEEs to talk to TEEs securely as well? Or is it always going to have to go to CAN to have communication?
No, you have to go through a CAN. Well, the setup of the initial trust has to go through a CAN. Then if as an application developer you want to have TEs or trusted applications talking to trusted applications within the system, that's something the developer can do. But the initial trust setup needs to go through the CAN.
But your protocol can't, your protocol doesn't have once you set up trust, here's how you talk to TE to TE, you don't have anything.
No, we don't have that right now. No, we don't have this concept yet of delegation of authority. Because fundamentally what you're talking about is, a CAN delegating authority to another party. We don't have that concept within the protocol. I think we'll get there eventually at some point in time. Okay? All right. Other questions? Very good. So feel free to reach out to me if you're interested in more discussions. Okay. Very good. Thank you very much.